Hi all, I'm Zhuoqing from Fudan University. I'm going to introduce the paper Sparsified block elimination for directed Laplacians, which is a joint work with Richard Peng. In this paper, we focus on solving linear directed Laplacian equations. That is, given a strongly connected graph G, its Laplacian matrix is defined as the odd-degree diagonal matrix minus the transpose of its adjacency matrix. Then for any given vector b, we want to find a vector x, such as Lx approximates b. The Laplacian matrix is very important in Markov chain. For example, with a nearly linear time Laplacian solver, commute time, escape probability, heating time, personalized PageRank vector, value iteration in Markov decision process can be computed in nearly linear time. And it can also be used to get numerical solutions to PDE by finite element methods. Also, with nearly linear time directed Laplacian solver, we can solve row and column diagonally dominant system in nearly linear time. And by polylog calls to directed Laplacian solver, the left and right scaling of M matrix can be found. Then M matrix equations can also be solved in near linear time. Among directed Laplacians, one of the most important class is Eulerian Laplacians. A directed Laplacian is Eulerian if each vertex in its associated graph has the same weighted in degree and odd degree. In addition, the symmetrization of Eulerian Laplacians are positive semi-definite. This seminal work has reduced solving directed Laplacian equations to solving Eulerian Laplacian equations. This shows that by adding a diagonal matrix to let L become RCDD and adjusting the right scaling with the diagonal matrix recursively, the right scaling can converge to the stationary distribution exponentially fast. Then, with the stationary distribution, directed Laplacians can be scaled to be Eulerian. So in this paper, we only need to focus on solving Eulerian Laplacian equations. We will use many tools from the following seminal works. The first one proposes nearly linear time directed Laplacian sparsifier and an almost linear time solver. And the second one proposes the first nearly linear time solver based on LU decomposition. This is the running time of our Eulerian Laplacian solver. To construct a good preconditioner, we use Schur complement specification to get a sparsified block LU decomposition. Schur complement specification is the main result of this paper and will be introduced later. After we get the sparsified block LU decomposition, the analysis follows the paper of LU decomposition-based Laplacian solver. The rest of the running time after we get a good preconditioner is about 2 log n factors additional to the number of non-zero entries of the Schur complement sparsifier. Using traditional numerical methods like Richardson iteration directly will lead to heavy dependence on the condition number. To get a more efficient solver, we need a good preconditioner M. Firstly, of course, M needs to approximate the pseudo-inverse of L. Secondly, we need to compute M times arbitrary vector x within near linear time. Then we can use preconditioned Richardson iteration to solve our problem. To construct such a preconditioner, we use block LU decomposition, which is a block version of Gaussian elimination. Gaussian elimination means we eliminate one vertex and replace it by the backlink from its in neighbors to its all neighbors. Block elimination means we eliminate a subgraph simultaneously, and the resulting graph is equivalent to doing Gaussian elimination to the vertex in the subgraph one by one. As we can see, eliminating a subgraph simultaneously is more difficult than eliminating a single vertex. The first thing is, which subset is easier to eliminate? A natural choice is almost independent side, which has many similar properties to a single vertex. In a Laplacian matrix, an almost independent side corresponds to a row and column diagonally dominant block, which is defined as follows. In the paper of LU decomposition-based Laplacian solver, a large, almost independent set can be found in nearly linear time with high probability. The method is very simple and has been used by Sparsified Laplacian solver for undirected Laplacians before. We can choose like half of the vertices, drop the vertices whose corresponding diagonal entries are not dominant enough, and we repeat this process until we find a large, almost independent set. We initialize S to be L, find an almost independent set F, then we use the RCDD submatrix SFF to eliminate the off-diagonal blocks. This yields the following factorization. Since the submatrix SFF is a 1 RCDD, we can simply use its diagonal as a preconditioner. Then we can compute the inverse of SFF times arbitrary vector x very efficiently. Then the problem has been reduced to the Schur complement of S. Since the subset F is very large, its size is proportional to n. The problem size will decrease exponentially fast. However, computing Schur complement can be very slow because it can be dense. So instead, we will find a sparse approximation for the Schur complement. The block LU solver we described above is illustrated in this page. The first thing of error analysis is to define what is a good approximation for Schur complement. The following notation of asymmetrically bounded is the same with the epsilon approximation in previous works. Given an asymmetric matrix A and a positive semi-definite matrix U, A is asymmetrically bounded by U if the image space of A and A transpose is in the image space of U. And if we normalize A by U, then the spectral norm will be smaller than 1. This is equivalent to the following inequality, which is very friendly to error analysis. So a natural choice is to asymmetrically bound the difference by the symmetrization of the Schur complement we want to compute. If we can get a good approximation to the Schur complement of Si in the sense of asymmetrically bounded, then by adding its symmetrization to itself, we can let the symmetrization of Si plus 1 be bigger than the symmetrization of the Schur complement of Si. Then we can define an approximate Laplacian, whose exact block LU decomposition coincides with the approximate block LU decomposition we compute from L. Then using the result from the paper of LU decomposition-based Laplacian solver, we can show the pseudo-inverse of the approximate Laplacian is a good preconditioner. Since the upper left block of each Si is a 1 RCDD, the pseudo-inverse of the approximate Laplacian times arbitrary vector can be computed to high accuracy very efficiently. So now, the problem has been reduced to get a sparse approximation of Schur complement in the sense of asymmetrically bounded. Here is the main theorem of our Schur complement specification. We use directed Laplacian sparsifier as a black box, and I will give more details later. Briefly, the running time only has one log n factor additional to the running time of directed Laplacian sparsifier. This additional log n factor actually comes from vector product sparsifier. For undirected Laplacian, this problem has been solved by this seminal work. For notational simplicity, we normalize the Laplacian and the adjacency matrix by the degree matrix. And we can define the partial block elimination operator as follows. It's easy to check that the Schur complement is invariant after a step of partial block elimination. Since the upper left block of L is alpha RCDD, we have that the upper left block of the normalized adjacency matrix has its spectral norm strictly smaller than 1. Then, if we apply partial block elimination recursively, the upper left block of the normalized adjacency matrix is getting squared and squared. So it will converge to 0 very quickly. Now, by setting k to be of order W log n, the upper left block of the normalized LK will be very close to the identity. Then its Schur complement can be computed easily by adding the sum of some vector products or equivalently some backlinks. However, the exact partial block elimination can be dense, so we will also use the following vector product sparsifier from the paper of almost linear time directed Laplacian solver. In the vector product sparsifier, the number of non-zero entries of the output matrix has about an additional log n factor compared with the input. To avoid the number of edges blowing up, we will also apply directed Laplacian sparsifier. We use directed Laplacian sparsifier as a black box and have three conditions for the output matrix. The first one is natural, and we use the second one to keep it alluring and guarantee that the upper left block of the normalized adjacency matrix converts to zero quickly. And the third condition is also natural, as we use the notion of asymmetrically bounded throughout this paper. Let me give you two examples of directed Laplacian specification which satisfy our conditions. The first one runs in near linear time. Firstly, do an expanded decomposition to the symmetrization of L, and then sample the entries in expander so that the error matrix can be asymmetrically bounded by the degree matrix of this expander. Then using Chickerson inequality, intuitively, the degree matrix can be bounded by the symmetrization of this expander. Then find patching matrix to fix the degree. And finally, the total error matrix can be asymmetrically bounded by the symmetrization of L. The second one is based on short cycle decomposition. It has longer running time, but has smaller number of non-zero entries. In this method, the number of edges will decrease exponentially until it reaches some threshold. Each iteration, the edges with high effective resistance are always preserved. Then do short cycle decomposition to the rest of the edges and drop clockwise or counterclockwise edges randomly. Our pseudocode of sparsified block elimination is illustrated in this page. Let me give a brief comparison with some previous works. Compared with the almost linear time directed Laplacian solver, their approach, very briefly speaking, can be regarded as squaring and the specification, squaring and the specification on the entire matrix. While the sparsified block elimination can be regarded as squaring and the specification on an RCDD block, which has much simpler structure compared with the whole Laplacian matrix. Compared with the near linear time solver based on LU decomposition, they use Gaussian elimination and eliminate one vertex at a time, while sparsified block elimination eliminates a large subset in only about double log n iterations. Intuitively, sparsified block elimination can have simpler analysis and faster running time. Let's discuss how to bound error accumulation in sparsified block elimination. We start from one-step error analysis. It has this form, and its right-hand side is the symmetrization of the approximation for the case partially eliminated Laplacian. So the first problem is how to bound this matrix. The second problem is about the robustness of Schur complement. In other words, in what conditions Schur complements are robust? That's because even if we can get a good approximation for LK, this does not imply directly its Schur complement is also close to the Schur complement of LK. The third problem is how will the errors accumulate with respect to K? As we will choose K to be of order O double log n, if the error accumulates exponentially fast, we will have too many log n factors. Next, we will show that actually the error only accumulates polynomially in K. For the first question, to better understand partial block elimination, we define the following augmented matrix, whose Schur complement coincides with partial block elimination. so it suffices to study the properties of this augmented matrix. In addition, its upper left block is also alpha RCDD. To better understand the property of the short complement of the augmented matrix M, let's look at the general directed Laplacians. Unfortunately, for general directed Laplacians, their short complements can be very unstable. By unstable, we mean the symmetrization of its short complement can be very different from the short complement of its symmetrization. Take unit directed cycle as an example. When we eliminate a large number of successive vertices, its short complement is still a unit directed cycle, but with a smaller size. However, for its symmetrization, the undirected cycle, its short complement will have some iterates being very small, when we also eliminate a large number of successive vertices. So when we eliminate successive vertices in a directed cycle, the short complement can be very unstable. In the paper of directed Laplacian solver based on LU decomposition, they show if the block we want to eliminate is alpha RCDD, then its short complement will be stable. As the upper left block of M is O1 RCDD, we can show the symmetrization of the partially block eliminated Laplacian of L, which equals the symmetrization of the short complement of M, can be bounded by the short complement of the symmetrization of M. Then, using the structure of M, we can show the symmetrization of the partially block eliminated Laplacian of L can actually be bounded by the symmetrization of L itself. However, if we use this relation directly, as we will choose k to be of order double log n, there will be too many log n factors. To overcome this, our strategy is to define even larger augmented matrices. Specifically, instead of bounding Lk by Lk-1, bounding Lk-1 by Lk-2 in a recursive manner. For each k, we can define a very large augmented matrix, such that Lk is its short complement directly. The above example is the augmented matrix that we construct for L2. Next, we show how to define the corresponding augmented matrix for larger k, and how to use this extended formulation. For each Lk, we define a sequence of Mik. We initialize Mkk to be Lk, and we construct Mik from Mi plus 1k so that Mi plus 1k is a short complement of Mik. Then Lk will be a short complement of M0k. In addition, for each I, all non-zero blocks of Mik are from the S partially eliminated Laplacian Li and the corresponding Ai. Then all non-zero blocks of M0k are from the initial L and A. Also, the upper left block of M0k is alpha RCDD, so its short complement is stable. Then we can use the structure of M0k to show the symmetrization of Lk can be bounded by the symmetrization of L. For the second question, we establish the following lemma about the robustness of short complement. If we are given an Eulerian Laplacian n and its perturbed version M, we want to bound the difference between the short complement of n and M. From this lemma, for example, if we let b equal epsilon and choose all the other parameters of the lemma to be O1, then we will show the difference between the short complement of n and M can be asymmetrically bounded by O epsilon times the short complement of U. To understand the conditions, maybe we can start from the case where the matrix U is a symmetric Laplacian, and it has the same diagonal entries with n, and the set F only contains a single vertex. Then the conditions will be trivial, and it's easy to check this lemma in this case because Short complement is equivalent to Gaussian elimination when the set F only have one vertex. And since alpha RCDD blocks have many similar properties with a single vertex, we can prove this lemma with more involved analysis here. For the third question, that is how the error accumulates with respect to K. Recall that Lk is a short complement of M0K, so we can naturally attach the errors to M0K to construct a perturbed version of M0K. And the approximate Lk is a short complement of this perturbed version of M0K. Then, to bound the difference between Lk and its approximation, it suffices to bound the difference between M0K and its perturbed version and consider whether the short complement is robust in this case. To bound the errors, we will also use the following kind of matrix. We name it repetition matrix. Remark that all the repetition matrix used in this paper have the matrix A here being symmetric. So why we will define such kind of matrix? By Cauchy-Schwarz inequality, intuitively, if we move some off-diagonal blocks onto the diagonal, we can make the matrix become more positive definite. We will also define a sequence of augmented matrices Qi to bound the difference between Li and its approximation. Recall that we attach augmented error matrices to M0I to define its perturbed version. By induction hypothesis, these augmented error matrices can be asymmetrically bounded by repetition matrices of M0I and Qi. Then, by defining Qk as a linear combination of the repetition matrices of M0I and Qi, we can bound the difference between M0K and its perturbed version by about O delta times Qk. By short complement robustness in this case, we can show the difference between Lk and its approximation can be asymmetrically bounded by about O delta times the short complement of Qk. By our definition, actually, Qk can be represented by a linear combination of repetition matrices of M0I. So Qk adopts many properties of the matrix M0I. So we can bound the short complement of Qk by the symmetrization of L. In this way, we can bound the difference between Lk and its approximation by about O delta times the symmetrization of L. Then it will be very easy to see that the difference between short complement of Lk and its approximation can be asymmetrically bounded by about O delta times the symmetrization of the short complement of L. This completes the proof. Thank you for listening. If you have any question, please feel free to contact us.